Okay. Right. Thank you for your for coming, and I will continue this tour through Flavour Physics at Hadron Colliders. Yesterday we talked about CP violation and the unitarity triangle, which is clearly a major pillar of these studies. Another major pillar is what is sometimes colloquially called rare decays, which basically is the study of flavor changing neutral current processes. So I will speak about those. At the end of my talk, I will speak about something. Well, here is my overview. So I'll explain to you what these processes are, what characterizes them. And we're going to be talking at length about, I picked out just two, which is BS to mu mu and B0 to mu mu, which is very much the golden channel, the ultra rare decay, which has driven these studies at the LHC. And then I will talk about transitions of the sort B to S, L plus L minus, which is encapsulated in the decay B to Kstar mu plus mu minus, but also related processes as well. And this is, as I say, it's the gift that keeps on giving. There's a huge amount of information to extract from these, and some very interesting results which have been keeping us amused for the last few years. And I will conclude with discussion of a process which actually is a tree level process. So it's not flavor changing neutral currents at all, but and nor is it rare, but it's not CP violation. And I think this is the best lecture in which to talk about it. It has connections with what has gone before. Okay, so flavor changing neutral currents are decays that proceed through higher order diagrams at tree level. I mean, these are processes that you could draw with at tree level, but with some neutral boson, but you'd find that that boson would not be obey the rules of the photon or the Z0, because it would change flavor. So these were these exist through box diagrams. We discussed those yesterday, but in the context of CP violation. But also these loop diagrams, these so-called penguin processes. So this, I know these have been discussed by others. I saw Kareem's opening lecture, but I'll say a few words about them. The nomenclature was introduced by John Ellis back in the late 70s, allegedly after losing a bet. This process, however you draw it, it's difficult to make it look like a penguin, but John's had a good go here. But the key point is it's a process which is suppressed in the standard model. The flavor changes from one down type quark to another down type quark, and radiated off there is a photon, a Z0 or a gluon. Now, most interesting measurements involve electromagnetic and weak penguins with a photon or dileptons, and these lead to rather precise predictions. So after the prediction of these diagrams, there was a hunt for them, and they were first discovered by Cleo back in 1993. And here you see the mass peak. And already the existence and measurement of this branching ratio was important, because what one can do is one can test the standard model prediction for the rate. And there's the possibility, of course, that a new heavy particle would actually exist inside this loop, and that would change the observed branching ratio. So the observation of this radiative decay by Cleo already actually constrained new physics models, in particular supersymmetry at that time, and they will continue to do so. And I know Kareem discussed this. So penguin decays are very naturally suited to E plus E minus machines. I talked about the difficulties that neutrals present in the hadronic environment, but still, that even given that, it is possible to study these at the LHC, and that's because the photon which comes out is reasonably hard. So if you have a B to K star gamma, for example, that's a two-body decay, so the photon can come out with transverse energies of 4 or 5 GeV. And this is very suited to seeing above background in the calorimeter. So as long as one is looking at an exclusive final state, we can do very interesting measurements at LHC B with these transitions. What we can't do is to study them inclusively, just to say that we are looking at a process B to S gamma at the quark level. We can't do that. We have to reconstruct the hadron to reject the background. So just to give one example of where we've been doing this, and when I give single examples for processes where the B factories have a big pedigree, I like to pick examples which are unique to the LHC. So I picked one with a lambda B decay, which of course is not accessible at the epsilon 4s. So this is quite recent, and one sees a very nice peak here, lambda B to lambda gamma, and one could actually then perform an angular analysis and learn about the polarization of the photon. Now, in the standard model, this is expected to be almost completely left-handed. So this parameter alpha gamma at the bottom, we would expect that to be very, very close to 1. I think the exact prediction is something like 0.95 or something. Anyway, you see that a measurement has been made, which is certainly consistent with this standard model value. The uncertainties are reasonably large, despite the nice size of this peak. So this is yet another example, a common theme throughout my lectures, of something which we'd like to return to with higher statistics. So at the LHC, we can look at processes with photons, but within certain boundary conditions. But something which is much more suited to us is the search and the study of the modes Bs to mu mu and B0 to mu mu. So these also can only proceed through suppressed loop diagrams. I've drawn one of them on the right here from the standard model. There are many others. And again, this is a process which could have a new physics contribution. So initially, the big hope was to, at the LHC, of course, was to find SUSY, and certainly supersymmetry is able to mediate these processes. And the expectation was that if it did that, it would enhance the branching ratio. Enhance it above what? Well, the standard model prediction of the branching ratio is at 4 times 10 to the minus 9. So this is a super ultra rare process. Okay, so this is suppressed by many things. It's CKM suppressed, it's also helicity suppressed. So it's a very rare process. And what's more, this 4 times 10 to the minus 9, it's something that's actually can be predicted really rather cleanly. The current uncertainty from theory on this is 10% or better. If you're looking for B0 to mu mu, that is suppressed even further. That's down by a factor of 30. So this was identified already back in the early 90s as a mode that we should look for. So at already, you see in this plot at the bottom right, already at the early E plus E minus machines, people were looking at least for the B0 to mu mu mode. And then as time went on, with Hadron machines, with UA1 and UA2, with the SPS and the UA1 experiment, and then later the Tevatron, it became possible to look for BS to mu mu there. And so we started with limits at the 10 to the minus 4, and these steadily marched down with time. Okay, and just before the turn on of the LHC, the Fermilab experiments were pushing the limits down to around 10 to the minus 8. So just above the region in which something interesting was about to happen. So certainly in the run 1 of the LHC, this was targeted as probably the highest priority in B physics to actually find this decay. So to re-emphasize its importance for constraining new physics, this is a historical plot back from David Straub in 10 years ago, but it shows, you see in this 2-dimensional space, BS to mu mu on the bottom, BD to mu mu on the y-axis. One sees this region in which different new physics models can inhabit, with a precise standard model prediction indicated by this gold star. And at the time this plot was made, the limit was excluding very, very little of this phase space. Experimentally, low branching ratio makes it a big challenge. There are many B decays that look rather similar to BS to mu mu, and rather similar is very dangerous when you're searching for such a rare process. You can have, for example, the combination of different semi-electronic decays mistakenly combined with each other. You can have a decay, a charmless decay, such as beta pi pi, where you've misidentified the pions as muons. So one needs sophisticated analyses, and this was an area where the machine learning analyses were pioneered at the LHC. So rather than making a cut-based analysis, there were the search and for this process relies on boosted decision trees. Actually, in the case of LHCb and CMS, 2 boosted decision trees, where you look for where you make a figure of merit, which is constructed from various input signatures. For example, you look at you compare the momentum vector of your reconstructed decay with the vector which goes from the primary vertex to the decay vertex, and there's many other ingredients that you feed into this boosted decision tree. On the right is its output from the Run-1 state-of-the-art LHCb analysis. You see a nice flat response for the signal and this steeply falling response for background. What I should emphasize is that these BDTs, wherever possible, are calibrated on data. For instance, using proxy decays such as B to K pi to simulate the signal. Okay, so this process was pursued with great intensity, and the actual progress was more rapid than people might have hoped. Shows you what happens when you get bright young people working hard. And indeed, already with the Run-1 data, an observation was made. This was actually made in a joint paper by LHCb and CMS, because I should really emphasize that this is a process which is also very well suited to CMS and indeed Atlas, something they can trigger on well, and they have a very high sample sizes, of course. And though the actual observation is made through consideration of all the events over all the BDT output, we can look into a bin which has a high BDT score for the signal, just to get some visual idea that indeed there is a signal there. And you see that there is a signal there. You see it peaking in this sort of reddy brown color. That is the BS to mu mu. And that comes in at a branching ratio of something like 3 × 10⁻⁹. So this is certainly seen with high significance, and it's roughly in accordance with the standard model. And on the left, rather interestingly, there is a hint of a B0 to mu mu. This is something, as you know, in the standard model should be down by a factor of 30, but at least in this early analysis, it seems to be peaking up and hinting at some rate somewhat higher than that. And on the right, you see the 2-dimensional plot where we plot both of these results. So these are certainly consistent with the standard model. The branching ratio of the signal BS to mu mu is not above the standard model, which people had originally hoped, but there is some tension with the prediction. So let's see how this evolved with Run-2 data and what the further prospects are. Because as ever, and I repeat my motto, in Flavour Physics, it's not good enough just to see something. We want to measure it as precisely as possible. This may look in accordance with standard model at first view, but with more precision, who knows what will show up. And indeed, LHCb has analyzed now the full Run-2 data set. And you see with LHCb alone, again, picking out a bin with a high value of this BDT to select the signal, it's very much there. Let's just pause a moment and realize what we're looking at. We are looking at a decay which has a branching ratio of 10⁻⁹. And we are seeing this very impressive signal. So this is really showing you the power of these experiments. The branching ratio now is measured by LHCb to just over 10%. And one notices that, again, to the left, that there is an indication of the B0 decay, but it's maybe not as pronounced in that early joint LHC-B CMS analysis. It's there with something like 1.7 sigma significance. And I show you again, you'll see several of these plots where we show the BS versus B0 in the two-dimensional plane. So we're sitting, we're certainly not above the standard model. We're a little bit below with BS to mu mu. And for B0 to mu mu, there seems to be nothing surprising going on at present. CMS have already also updated their results. I think so far, just including the 2016 data. So there is a nice peak. I should remark that there's an additional systematic error here from so-called fragmentation. It's important when setting the branching ratio because you normalize what you see to control channels of the sort, if I go backwards, BS to J psi k or B0 to K pi. So you compare what you're seeing to the rate of those processes. And for something like B0 to K pi, you need, that is a B0 decay. You're looking at the BS decay, so you need to know the relative fragmentation rates of B0 and BS. So this is something which has to be measured. It has been measured by LHC-B, but that's been measured within their kinematic acceptance. So CMS are more central, so one has to extrapolate into that region. And this process brings some uncertainty, but it's small. Again, we see this in the two-dimensional plane. Let's not dwell on this, but one does see the picture is rather similar to LHC-B, with the measurement being a little lower than the standard model, BS to mu mu, but certainly compatible with it. And Atlas also, so they have a signal, it's clear, but one might note another feature of these plots. Now, if I just cycle through them, you see that the width of the peak for Atlas is quite broad. If I go back to CMS, that's better, that's narrower than Atlas. But LHC-B, you see that's more skinny. So in LHC-B, one can definitely resolve the BD and BS contributions. For CMS, there's some hope of doing that, but for Atlas, they lie on top of each other. So this comes from the mass resolution, the resolution on the momentum of the tracks, which is important in flavor physics, because the narrower your invariant mass peak, the crisper you can distinguish your signal and reject background. But still, Atlas have this signal. Nothing for. So if we let's put things all together. So I do this here. Okay. So this is a combination across all of the LHC experiments. It does not have the latest LHC-B data in it, but that is rather similar qualitatively in central value to what went before. So the overall picture, when this is added, won't change very much. The contours will just sharpen a little. And again, one sees that the measured value of BS to mu mu, that branching ratio, is compatible with the standard model, but it's lying somewhat low. Okay. No sign of B0 to mu mu yet, but the central values of whatever signal is there seems to be compatible with the standard model. But in this plane, there is tension. The overall tension is something like 2.1 sigma. So initially, we were looking for an enhancement of the branching ratio above the standard model, because that was the sort of natural thing to look for, given the smallness of the branching ratio. But now it becomes equally interesting to consider the implications of having a lower than expected branching ratio. And this can be certainly accommodated, and there are many models in which this can be fitted for. And we will look at a few of these when we get to the latter half of the talk. But this is a measurement which is certainly worth watching more carefully as more precise results emerge. So this is to say that this result, I mean, on the top right, you see a somewhat updated, though not state-of-the-art plot, just updated with respect to that David Straub 2010 plot I showed earlier, that this measured branching ratio has cut into big swathes of new physics space. So it's been important in excluding certain high tan beta SUSY models. On the bottom left, there is a plot which is in the usual two-dimensional form. One sees many different, the blue and the green here indicate various possible new physics models with new sources of flavor-changing neutral currents. One sees this big band, the top left, this egg here was the measured value at the time this plot was made, which was about 5 years ago now. But one sees if one can improve these measurements significantly, and shown here is what one might get to with the LHCb second upgrade, then you can really home in and you know, distinguish, be very, very, very sensitive to physics beyond the standard model. So beta measurements are essential because we're still far from the theory limit, and that will improve. And in particular, trying to find B0 to mu mu and to measure the relative branching ratios of the BS to the B0 process. This will be very important. That's very clean and it's very sensitive. So somehow that's the next step in the journey. But before leaving this topic, we can say that there's, as we get more and more data, there are more things we can do with these decays. We don't just have to measure the branching ratio. We, for instance, can measure the lifetime because it's made of BS and BS bar mesons. That lifetime is a non-trivial parameter, and it has sensitivity to a term here, which I call A mu mu delta gamma, that is one in the standard model, but can take other values in non-standard model scenarios. So this is, so one has sensitivity to new physics in ways which are not probed just by the branching ratio. And so improved, so measurements of this lifetime will be important. And indeed, measurements have been made already by LHCb and CMS. You see them here. Let's emphasize again, we're looking at a decay with a rate of 10 to the -9, but we now have sufficient sample sizes. We can study the lifetime evolution of these decays. And as time goes on at the LHC, it will be very interesting to see how these distributions sharpen up and improve in precision. Okay, so on to the second major topic of the lecture, and that's looking at B to S, L plus, L minus transitions, where L indicates a lepton. Indeed, B to D, L plus, L minus is equally interesting, but these are even further suppressed. So these will not be in the foreground for our discussion today. So these decays, BS to L plus, L minus, they're not ultra rare compared to BS to mu mu, but they do provide an exceedingly rich set of observables to probe for new physics effects. And these are sensitive to non-standard model helicity structures and more. So I put on the top right some of the loop diagrams which drive these decays, and you see that there are many of them. These involve standard model particles, but of course, we are hoping that there will also be new physics particles contributing. So there's many realizations of this quark transition, but the poster child is a B to K star L plus L minus, with the K star decaying to K pi. That's because it's quite easy to reconstruct 4 charged tracks, and you get a 4-body final state that can be characterized in terms of 3 angles, and then you can analyze the full kinematics of this final state decay. And this is usually done in bins of the invariant mass of the dilepton pair. So in the plots which you're going to be seeing from now on, a lot of them will have along the x-axis q squared. So this is the q squared of the dileptons produced. Okay, so several angles involved here. So this means that the differential cross section has this very rich structure. This is not something I'm expecting you to note down or learn, but one sees in here that one sees FL, which is the longitudinal polarization or the fraction of the longitudinal polarization of the K star. One sees something called AFB, which is the forward-backward asymmetry of the dilepton pair in the B meson frame, and you see other coefficients, rather uninspiring names, S3, S4, S5, and we'll come back to this. But the take-home point is this is a very rich system, that there's many things to measure. Okay. So let's think about some, let's just pause and have some experimental considerations. So I've been talking about K star L plus L minus. What we actually reconstruct is K pi L plus L minus. So that means that though it's dominated by the K star 892, there are in principle other contributions, in particular those S wave contributions, which have where the K pi does not come from this K star. These are important, and these so you need to work out how these affect your observables, and this has been done and is being done better. We won't discuss it here, we don't have time. In the PP environment, like the LHC, it's easier to reconstruct muons than electrons. So unless I say otherwise, measurements you look at will be made with the dimuon final state, and this is important. And then in these decays, again, you have to wrestle with the presence of QCD. Clearly, it's much more important than the fully leptonic decay BS to mu mu. And in particular, you have to worry about the uncertainties coming from the form factor, and these affect the predictions of these coefficients. But these uncertainties can be suppressed by changing to a set of optimized observables. So on this previous slide, you see these S's up to S9. What one sees here are so-called P observables. I'm afraid the nomenclature here is rather dull. So you have P observables and indeed P prime observables. And these are mixtures of these S observables and normalized by things involving the longitudinal polarization fraction. You might ask, what do these mean? Well, they're hard to visualize, but practically they're important because they have reduced form factor uncertainty, so they should be much more robust. So they can be predicted in the standard model with rather small uncertainties. Also, they can be interpreted well in terms of new physics properties. But in terms of visualizing what they mean inside the detector, that's beyond my ability, I'm afraid. But this is actually quite good from a systematic point of view. In measuring any of these events, you're not dominated by events in some particular region of the detector or phase space. They come from everywhere. So intrinsically, these measurements are experimentally, systematically robust also. Okay, so now to view these, the progress here in historical terms. So this already at the time of the B factories, it was known these decays were of great interest. At that time, people didn't care so much about these S and P observables. They focused on this AFB, this forward-backward asymmetry of the leptons in the B0 frame. Again, I said we measured these as a function of Q squared of the dilepton pair. And Belle, for example, were able to chalk up something like 250 candidates, this involving muons and electrons, I think. So here is the forward-backward asymmetry from Belle plotted again as a function of Q squared. So this initial result was already quite interesting because you see that measured asymmetry all lies above zero, whereas the expectation in the standard model is that the asymmetry should start negative, go upwards through a zero crossing before asymptoting here. So what we are seeing is some hint of non-standard model behavior. So there was some great hope and anticipation how this might evolve with the larger data samples that would come at the LHC. Also note on these plots that we're looking at the variation of Q in the invariant mass of the dimuon pair. There are these two yellow regions where there's no data points. these yellow regions, if you look at the values, these correspond to the J psi and the psi prime. So these are resonances. There, the diagrams mediating the process are very different. They're tree-level diagrams. They're driven almost certainly by the standard model. So it makes no sense to try and actually measure these observables in those regions. So you'll see that those regions are cut out from all the plots that I will exhibit. Okay, so how does this forward-backward asymmetry, how does this look when you go to the LHC and you have the statistical might of the Hadron Collider? Okay, so here is a result from LHC Run-1 with early Run-2 data. We have 4,600 signal candidates, so many more than Belle did. Again, we plot against the invariant mass of the dielectron pair. We exclude the J psi and psi 2s regions. And what you see is, so sadly, this very non-standard model behavior seen with the very early B factory data is not substantiated with the more precise data set. What one sees is data which, again, is going low, then up through a zero crossing point as predicted in the standard model. But it's interesting to note that the agreement with the standard model is not perfect. So there seems to be some tension, particularly in these low Q-squared bins. Another important remark I should make before we see many more of these plots is I keep saying the standard model. This is what one has here is a prediction made by theoretical groups. Though these observables have been constructed to be reasonably clean, they do have uncertainties, and those uncertainties, is a matter of judgment. So they'll be different from group to group. So you see a prediction here from ASZB. So that is a group. Afraid I can't remember who they are, but it is the reference will be in the paper I list here. But you'll find that other groups will come up with slightly different predictions. So I will glibly say standard model, but there's more to it than that. But we see that the LHCb measurement is roughly in accordance with the standard model, but it's not perfect agreement, but it's precise. So now let's look at some of these other observables I spoke of, ones which are particularly constructed to be more robust than this, so with lower uncertainties. So the one which has attracted the most attention is the so-called P5 prime. So again, I apologize for the boring nomenclature, but here one sees the most recent measurement of something which was already seen with early data and has stayed there like a bad smell. One sees that, again, you see how the prediction is expected to evolve in these beige boxes. Again, I call this standard model, but it's the prediction from this group of theorists here. And one sees that the data is not agreeing with this, that there is tension, significant tension, particular in these two bins just below the J psi. And the level of this tension is something like, well, it's over 2.5 sigma in both of these bins. Okay, so this is something which has persisted, and it does not look to be a statistical fluctuation. This looks to be genuine. So this is maybe I've been driven by physics which is beyond the standard model, but something we should work hard to exclude is just that we don't have the right handling or understanding of the standard model prediction, in particular the QCD uncertainties, things coming from things called charm loops. These may affect these predictions. So a lot of work is also going on to try and constrain these uncertainties from the data. But just this has been shown by LHCb, so other experiments have come and measured these things. None of these experiments have the same precision as LHCb, and so this plot is rather busy, but I hope you can make something from it. The LHCb data here is actually from a slightly earlier publication, but it has very similar behavior. But certainly in this region, which is causing the interest, one sees that all of the experiments with one exception seem to be seeing the same thing. Atlas is very high. Belle is right in there. CMS here is low in this bin, and much more in agreement with the standard model, but the statistical uncertainties are large. So I think, again, I stand by the statement that in this measurement, at least, I don't think there's anything statistical going on. I think we do have a definite tension with respect to this prediction. Okay. I mean, one can go to other channels. So we've been concentrating on Kstar Mu Mu, where that's the neutral K-star, which decays to 2 charged tracks. You can go to the charged K-star, and LHC B have done this. There, the statistics are much lower because you have to deal with the neutrals in the final state, but qualitatively, the picture is very similar, you can see. And I've been emphasizing P5 prime. There are these other observables, and one, when you study them as a whole, one finds that indeed there's a tension in these other observables. This can be exposed in a so-called Wilson coefficient fit, about which I will say more very shortly. A consistent output has come from analysis of BS to phi mu mu, for example. So this is a very, very interesting system. And the other remark I want to make is to come back and say, well, these measurements were all made with dimuons. I've been listing them as a K-star lepton plus, lepton minus. What happens if you try and make the measurement with electrons? So this has not yet been done at the LHC, but it's been done by Belle. And what one sees there, I mean, the muons and the electrons are consistent within their uncertainties, that we must say first. But one does note that the electrons here in red, the muons here in red lie above the electrons in green. So given what we're about to discuss on the next couple of slides, this behavior is intriguing, suggesting that maybe the electrons have more standard model-like behavior than the muons. But from this plot alone, we in no way can make that statement with a straight face, because the statistical uncertainties are large. These are all, we've talked about these very cunning observables, these optimized observables, P5 prime. We can then take a step back and look at something much simpler. We can say, okay, I don't really know what those observables mean. What about if we just look at the differential branching ratios? So this slide shows the differential branching ratios, not just for Kstar Mu Mu, which is the top right, top middle one, but for a bunch of other processes, and I'll let you read them yourself. So again, these differential branching ratios are plotted in bins of Q squared, and one notices that in all cases, the measurements are incompatible with the predictions. There's a strong tendency for the low Q squared differential branching ratios to be lower than the prediction. So this adds to the intrigue, but again, is something we should take with a lot of caution. The differential branching ratios are certainly not robust against these QCD uncertainties. There's a reason we go to optimize the observables, and that's because they are cleaner. These predictions are not clean. You can see in general the size of the error bars are larger than we've been looking at, but still one cannot ignore that this behavior is out there. So what we'd like to do is to maybe short circuit the discussion by going to perhaps observables where we don't have to have this caveat about the theory uncertainties. We'd like to go to an observable where the theory uncertainties are negligible. Do such observables exist? Yes, they do. They exist if you go and make a lepton universality test. So here we look at observables. Ideally, we look at all observables, and that is part of the program for sure. But the first observables we are looking at are the respective rates, and we look at these for the muons compared with the electrons. Okay, so if we compare that rate in a given region of Q squared, there should be a completely negligible theory uncertainty. The standard model up to will say that what you expect is a rate of a relative rate, a ratio of these rates, which is unity. Okay, there are very small deviations from this due to phase space effects at a low q squared, but to all intents and purposes, you expect unity. So there have been measurements made of the in the low q squared region of the respective rates of b to k mu mu compared to b to k e plus e minus, and we call this observable RK, and an analogous observable involving k star L plus L minus, which we call RK star. So in the standard model, we expect both of these observables to be 1, and this is what we have at present. So the top one is from is RK, the bottom one RK star. RK has been analyzed using the full data set, RK star with just the Run-1 data. And what you note immediately is that both of these are a significant number of standard deviations away from the standard model expectation. So this is very intriguing, and it has excited a huge amount of interest. Electron universality is one of the pillars of the standard model. There are other decays apart from B to K star plus or minus, with the neutral K star, and B to KL plus L minus, which have been analyzed. So you see at the bottom here in black, and now here you see measurements made with these processes K star plus L minus and K short L plus L minus. So the statistical precision is worse than what we've been looking at because they're experimentally more challenging. But again, you see that the measurements available from LHCb are less than 1, though not at a very significant level. And indeed, measurements have been made for lambda B decays to the analogous process. Again, we don't have a statistically significant discrepancy, but the central value is less than 1. Maybe we should just say a couple of words about how we make these measurements, just so you understand experimentally how it is done. So I will focus on our RK star. So this, for those of you who attended the tutorial yesterday, we looked at a question where we studied these experimental details in a little more with a little more focus. But anyway, let me try and tell you the main points here. So firstly, your precision is certainly limited by the size of the electron sample, which for this Run-1 measurement was something like 100 decays. The muon sample is much larger. So you have, to the left here, you have the muon B peak, and to the right, you have the electron B peak. And you also see the electron peak has more background, it's wider, there's bremsstrahlung effects to correct for. So it's a challenging thing to reconstruct. So to try and make the measurement more robust, you might worry about, how well do you know your electron identification efficiency? How well do you know, in particular, the electron identification efficiency? Well, we think our Monte Carlo is quite good, but we can take out this consideration as a first order effect by actually normalizing our result to the respective rates of the decays to muons and electrons from the J psi mode, so from the resonance region. This is the region where we expect no new physics. We expect the ratio there to be 1, but the identification, the actual properties of the electrons and the muons should be very, very similar to those of the region we're interested in. So this is an important control mode. We indeed observe that this ratio of the muons to the electrons in the resonance region is 1, and it is compatible with 1 throughout a whole range of kinematic variations. You can vary the momentum of the electrons, the pseudo rapidity in which they're detected. We always measure this ratio to be 1 for the J size. So this gives us confidence in the measurement, at least that the efficiencies are under control. Okay. Right. Maybe now I will pause and finish the actual experimental discussion and just let us scratch our head and wonder what this means. We've seen many puzzles in this B to SL plus L minus data. Can we make sense of these? So qualitatively, you could explain them by saying, hypothesizing that B to SE plus E minus largely obeys the standard model, but the new physics intervenes for B to S mu plus mu minus at low Q squared. So that's a qualitative statement, but that would explain pretty much everything we have seen. But a more quantitative analysis can be made in the context of effective field theory. So here, this on the left you have the real theory, and on the right we have the effective theory. So this is very analogous to the Fermi theory, which can be used to describe beta decay. You have a effective vertex here, and these are described by in a so-called operator product expansion with these operators here, and CI. These are the CI are the Wilson coefficients. So these describe the, I mean, there's a whole bunch of them, and we'll talk about C7, C9, C10. They describe different types of interaction in a rather model-independent manner, and these are, depending on which flavor-changing neutral current process you're looking at, they will depend on a subset of these parameters to a greater or less degree. So you see that BS to L plus L minus depends on C7, C9, C10, and the primed versions of those, whereas B to L plus L minus, which is responsible for BS to mu mu, that depends on C10 primed, and this other coefficient here. So these are calculable in the standard model. So what one can do is you can actually take all the observables we've been looking at, both from BS to L plus L minus, but also from BS to mu mu, and you can put these into a global fit of Wilson coefficients. And this has been done by many people. I've given you just one example here, but whichever example you dial up, you'll get a rather similar conclusion. Now, so if we look at the actual bottom line of this conclusion, the best fit you get for these Wilson coefficients, it is in all cases it's inconsistent with the standard model. So that's the first thing to be said. But it includes all measurements. So some of these measurements might have bigger experimental systematics than others, which maybe have been wrongly assessed. And some of these measurements have theory uncertainties, which some people would argue with, and some of the measurements have pure theory uncertainty, such as BS to mu mu, and also the electron universality measurements. So it's important to distinguish the contribution of each of these. And you see in this plot, so what this plot shows C9 universals, that's assuming the C9 is the same for the electrons and muons, against plotted against a shift in the parameter C9, which is set equal to that for minus C10. So this is all a little arcane, and I don't want to, in this presentation, get into exactly what this means. But what you should know is the standard model should be sitting here at 0, 0. And you see that you see a horizontal band, almost a band in blue, coming from the electron universality violating observables. You see a band coming from BS to mu mu, and then you see this egg here, which is coming from all this P5 prime stuff. Okay, so you see two consequent. I mean, again, what does this tell us? Well, you see that these bands are pretty much consistent with each other, not perfect, but they line up quite well, and they give you this right-leaning egg here. You see this egg is quite a long way away from the standard model. This is already remarked on, and this has been achieved by allowing for a new physics shift for the muons alone, which is of the opposite sign in C9 and C10. A modest, and for in electron universality case, this is the horizontal axis. There's essentially no shift at all, maybe just a modest one to the left. But you'll see other fits which play with different possibilities of varying the Wilson coefficients. And there are other explanations, but this is somehow the favored fit. So let's step back from Wilson coefficients. I mean, what could this mean in reality? Well, this could be explained by, for instance, new bosons, high mass Z prime, or even leptoquarks, which at a vertex would link both leptons and quarks. So these are very much new physics, and these particles could be within reach of the direct detection of ATLAS and CMS. So people are actively looking for them. So to conclude this discussion of BS to L plus L minus, and indeed B to D L plus L minus, I think we see that something is interesting afoot, but we need better measurements. We would like a full run-2 analysis with the dimuons on this P5 prime and the other optimal observables. This is being worked on, it's not come yet. And you'd like actually equivalent studies with dielectrons, because if you saw a different behavior for electrons in P5 prime than for muons, this would be very compelling. You would like to make these lepton universality results, you'd like to see those made in different Q² regions. I just showed you them made so far we just made them at rather low Q². And indeed you'd like other measurements from other modes, and for instance BS to phi L plus L minus. These measurements are coming, indeed updated measurements of RK are coming, and the full RK star results are coming. So I hope these will be available soon and should shed some light on what's going on. You'd like results from other LHC experiments. Low PT electrons are very tough for ATLAS and CMS, but maybe something can be done. And you'd like results from Belle II. My personal opinion is that even if the current anomaly dissipates, the story has been very useful for focusing attention on one of the less well understood features of the standard model, that is lepton universality, and also illustrating the power of a complementary ensemble of measurements. And whatever happens, these studies of BS to L plus L minus are sure to remain of great interest. I've almost done. I just got a couple of slides because I want to actually mention another important process which can be looked at the Hadron machine, but has been pioneered at the B factories. And this is looking at the tree level process, B to C L plus neutrino. So at the standard model, so the amplitude of this is tree level. It's not a flavor changing neutral current. It's not a rare decay. It's one of the essentially the most common way a B can decay. But there are issues here, and these issues have persisted for 10 or 15 years. That when we measure this process, for instance, in B to DL nu or D star L nu, and we look at the process with a tau compared to that of a muon, we don't get a result which is consistent with lepton universality. Here, lepton universality, you might know, in the previous discussion, it was 1 for the ratio. Here it's not 1 because the tau is massive, so there's phase space effects which need to be accounted for. So the standard model prediction in this plane, you're talking about a value of 0.26 for our RD star and 0.3 for RD. That's what you expect. So though it's a tree level process, it was first looked at because if there's a charged Higgs out there, that could also give this final state, and you would have sensitivity to this charged Higgs if it was light enough. Here you see a whole swathe of measurements made by Barbar and Bell, and you see that these are combined, and also LHC B, which I'll speak about. The red egg is the combination, and it's about 3 sigma away from the standard model. So there's a long-standing discrepancy here. The actual way the discrepancy evolves with Q² and things actually indicates that it's unlikely to be due to any charged Higgs, but things such as leptoquarks could explain it. So it's rather a stretch to explain it in the same way you'd explain the B to SL plus L minus case. Now, the missing energy from the semi-leptonic decay means that these measurements are ideal for the B factories, but competitive studies have come from LHCb in a variety of channels. For instance, our D star has been looked at both with the tau decaying to in a muonic manner and decaying to a 3-prong final state, 3 pions. This measurement is very difficult to do at the LHC, though it's the decay is very abundant. The missing energy means there's lots of background, and there's no way of isolating a very pure sample. Whatever variable you used, the signal in the background tends to line up in each other. So we used a multivariate boosted decision tree, and then we fit the Q² of the lepton system and the tau lifetime in different bins of this BDT. And you see on the right here, on the left, the tau of the lifetime of the tau and the Q², and these are coming down from top to bottom, increasing signal purity in terms of BDT output, and the signal here is in red. So at the end, you get a rather enhanced signal, but the statistics are rather low. Anyway, these results have been made just with run 1 data. So there's these 2 results, and I show you where the bands lie. One is high compared to the standard model, one is consistent with the standard model. They've been very difficult measurements to make. We would like new measurements with run 2 data. They'll be coming soon, and hopefully these will have sufficient precision to actually really say something about what's going on here. And again, at the LHC, we can also make measurements involving particles not accessible to the B factory, such as lambda B and even B sub C mesons. And I point you to these proof of principle measurements, which are linked from these papers, which will, in time, when they're improved in precision, add to this story. Okay, so it's certainly time for me to conclude. Some of the most powerful probes for new physics, which are sensitive to the highest mass scales, are from studies of flavor changing neutral currents. Very many studies are underway at the LHC, some with an intriguing status, and the most powerful and interesting concern BS to mu mu and BS to L plus L minus. Also of interest is this tree-level process B to C tau nu, which has puzzled the community for many years. Very challenging at Hadron Colliders, but as I've just flashed in front of you, sensitive measurements can be performed, and we hope still more sensitive ones still. So in all cases, more data and more precise measurements are required. At that point, I conclude the lecture. In the one later this afternoon, if you still have the stamina, I will be talking about charm physics, a real province for the Hadron Collider, and also future outlook. Thank you for your attention.
Thanks, Guy. I have time for a few questions if there are any. Yeah, Gagan, go ahead.
Yes, so thank you very much for an excellent talk, guys. So I have one small question, very naive question, and one comment. So question is about slide number 41. It is always intrigued me, but I think probably your cartoon answers that question, but I just want to be sure about it. So this cartoon you have on the left-hand side, very nicely that how the be going to the star tau nu. So I always wanted to understand that why RD is more challenging for LHCb. So am I understanding correct that that because you don't have this the vortexing for the B meson, like the D is flying certain distance and then you don't have the slope ion. Is that right? I mean, why the RD is more challenging for LHCb compared to RD?
Well, yeah, it must. Yeah, okay. Well, I'll turn this round. I don't know why this measurement is so easy at the B factories. How do we do it? We have a lot of background. I mean, we just the missing energy just stings us. Stings us more than it does for you. Yeah, I mean that's a.
I see.
Good question.
So it's equally right. So RD star versus RD, there is no particular thing you think? I mean, if RD star is viable, I mean, why not RD? So like, so I thought maybe experimentally RD is more challenging at LHC. That's what I thought. But
well, you're right. We should be able to measure RD, and we are measuring RD. In fact, I can tell you there's a combined RD star RD analysis. This is actually one of the longest running analyses on LHCb. It's been going on for 5 years. It's been going on so long that actually one of the proponents of it has transitioned from male to female during that time. It's a beautiful analysis, and it's going to be ready very soon. So you can you know, it's in the final stages of review, so there will be a RD star RD measurement coming out. I really hope within this calendar year, maybe the summer.
I say maybe, right. Okay, just a suggestion. This is about the what you showed Belle II and CMS other LHC experiment. I think couple of slides back, maybe. So I think from CMS side particularly, I think this you know, the P5 prime. Yeah, this one. Right. Yes. So clearly, I mean, electron, as you know, it is even more challenging for CMS. So yeah, I was thinking of P5 prime. Like Sanjay will be giving a talk, I guess, in the you know. So I think that will be also very interesting. I mean, particularly we have an upgraded muon detector with this gem and another thing and the trigger. So I guess that will be also quite interesting. I mean, I don't know about Atlas, like how the muon sensitivity will increase, but particularly for CMS, I know it will be quite.
Yes, and I'm aware of that, Gagan. So I will, sort of data you have, but also high luminosity LHC upgrades as well. That there are good prospects here. So we can really hope for nice results to come from you and Atlas, but I was, you know, let's hope so.
Any other questions? I just had with the tau decays, is there any prospects of any of these rare decays with taus? Like, or even lepton flavor violating ones, perhaps with one muon and one.
Well, yes, I didn't. Indeed, I made a decision not to over egg my lectures. I didn't include those, but tau to 3 muons. That there's already a couple of LHCb measurements of that, and they have the most recent has a precision which is rather similar to that of the B factories, and with the high luminosity LHC, you could hope to get that down to the 10 to the -9 level. If things go well at Belle II should still have the best measurement, but I hope things do go well at Belle II, but who knows? But we are certainly in a sensitive region, and also measurements have been performed there by CMS as well.
Also, can you please mute?
Yeah, I've done that.
Did you hear that?
Yes, yeah. So the tau decays. I was thinking more of things to do with like BS to tau mu.
Oh, sorry. Oh, okay. Yeah, well, there's been a search for BS to tau, and that will. Yeah, no, it's very important to look for these decays. They could certainly be enhanced if there's anything in this. There's anything true in this lepton-quark business. Also, lepton flavor violating decays, BS to mu tau, for example. These are being looked for. There's a recent measurement. I'm not sure if it's public yet, but yeah, there's a lot of activity there. Yes.
Okay. Thank you.